All right, let's talk about something that I think every single person in software is feeling right now: complexity. It's getting out of hand, especially with AI now pumping out code faster than ever. But what if there's a better way? What if we could stop fighting our code bases and start, well, understanding them, using the language of physics? It's a pretty wild idea, so let's get into it. You know the feeling, right? You make a tiny change over here, and suddenly something completely unrelated on the other side of the app just breaks. A simple feature turns into this epic month-long saga. It seriously feels like the code base has a life of its own, and it's actively working against you. Well, the core idea we're going to unpack today is that, you know what? That feeling isn't just in your head. It's the result of real, measurable dynamics at play. So, to really get a grip on this, we need to change how we see things, like fundamentally. We have to stop thinking about software development as just a checklist of isolated events. A bug fix here, a new feature there. That's the old way. The new way is to see the whole thing as one continuous system. A system with flows of energy, with things called attractors that pull the code towards certain states. In this view, bugs aren't just little defects. They are symptoms of the entire system's behavior. And our processes, they're not just a bunch of rules to follow. They are the forces that actually shape the entire energy landscape of the project. Okay, so how do we start thinking like this? This is where it gets really interesting. We're going to borrow a powerful metaphor from classical mechanics. We're going to start treating our codebase not as a pile of text files, but as a physical system that has its own forms of energy. First up, we have kinetic energy. We'll just call it T. And just like in physics, this is the energy of motion. Think of it as a measure of how much your codebase is moving, how fast it's changing. We're talking about things like code churn, major refactors, big API shifts, basically any activity that makes the system move and shake. And on the other side of the coin, we have potential energy, or V. This is the energy that's stored up in the system's structure. It's all about the constraints that give the system its shape and really its stability. So things like a strong type system, a solid test suite, clear design docs, all of these things build up potential energy. They create a kind of landscape that helps guide all that motion in a stable, predictable direction. And this brings us to the absolute core of the idea. We can actually combine these two things into one single number. In physics, it's called the Hamiltonian. Let's call it H, but forget the fancy name. For our purposes, just think of it as the project's total stress meter. It's just the kinetic energy plus the potential energy. It's one number that tells you how much the system is moving and how much its structure is being strained. And when that number, H, starts to climb, that's when you know you're heading for trouble. Now, let's be totally clear here. We're not talking about calculating this stuff in joules or plugging your Git history into a particle accelerator. That's not the point. The power of this is as a mental model. But you can absolutely build real heuristics that approximate these values. You could measure code churn to get a sense of T, and maybe test coverage or type strictness to get a sense of V. It gives you this powerful new lens to see your project's health. So this is where it gets really, really powerful. Once we have these two numbers, T for motion and V for structure, we can actually plot them on a graph. And when we do that, we get a map. It's a kind of phase diagram that shows you the true state of your project. And more importantly, it shows you where it's headed next. And I bet you've lived in every one of these quadrants. High motion but low structure, that's cowboy chaos, where everyone's shipping fast and breaking everything. Low motion and high structure, that's frozen bureaucracy, where process has killed all progress. The sweet spot, the place we're all trying to get to, is that top right, resonant flow. This is where you have a ton of activity, a ton of energy, but it's all happening inside a stable, well-defined system that keeps everything productive. And this is the real game changer. Think about most of our metrics today, like bug counts or story points. They're all lagging indicators. They tell you what happened last week. This approach, this gives you predictive power. It lets you see when your project is drifting toward a danger zone, like cowboy chaos, before all the pagers start going off. It's the difference between looking in the rearview mirror and looking at a map of the road ahead. Okay, so we have this energy map of the project. Now let's zoom in a bit and look at the structure itself. To really understand how a healthy system holds its shape, especially under pressure, we can borrow another amazing concept, this time from architecture and biology. It's called tensegrity. Tensegrity is this really cool principle you see everywhere, from massive bridges to the actual cytoskeleton inside your cells. The idea is you have these rigid parts, these struts that are under compression. But here's the wild part. They don't even touch each other. They're held in a perfectly stable shape by a continuous web of cables that are all under tension. It's this beautiful balance of push and pull. And the analogy to software is just, it's perfect. The struts, the rigid parts holding the load, well, those are our concrete artifacts. That's our code, our APIs, our database schemas. And the cables, that tension network that pulls everything into a coherent shape, that's all of our constraints. It's our tests, our API contracts, our type systems, our team standards. A healthy code base isn't just a floppy mess. It's pre-stressed, with these two forces held in perfect balance.
Okay, I know what you might be thinking. This is all fascinating theory, but how do we actually use any of it? Well, let's walk through a super practical workflow that shows how you can manage this energy, moving from these abstract ideas to something you can do tomorrow.
So let's look at this workflow. It's called Coding Like a Surgeon, and it's a perfect example of how to manage kinetic and potential energy. The whole idea is to separate preparation from execution. You make sure you never just dump a huge amount of chaotic, unplanned energy into the system all at once. So check out how the energy is managed here. Step 1. An AI agent writes up a super detailed plan. Notice we haven't touched a single line of production code. This is all about building up potential energy, that V. We're creating understanding and constraints. Then, in step 2, the human developer reviews that plan, getting their mental model in sync. And only then, in step 3, do they perform the live surgery, making these very precise, controlled edits. That's a focused, careful injection of kinetic energy, or T. And the key insight is just so simple, but it's so powerful. You build up all of that potential energy, all that understanding and structure first, before you start injecting the kinetic energy of actual code changes. When you do that, the changes you make are guided and constrained. It keeps everyone's mental model perfectly in sync with the code, and it helps prevent the chaos that comes from, those monster pull requests that we all absolutely dread reviewing. And this really leads us to the ultimate goal. The point isn't just to observe our software's physics from the sidelines. The point is to become engineers of it. We want to be able to actively design the energy landscape of our projects to get better results. At the end of the day, what we're trying to do is design our processes and our tools so that the path of least resistance, the easiest, most natural way to do your work, is also the one that leads to healthy, stable code. We want to create systems where tired humans and, frankly, lazy AIs just sort of fall into the pit of success by default. And with this framework, you suddenly have a whole new, much smarter set of questions to ask about any change you want to make. So you can forget asking, does this increase velocity? And start asking things like this. Is this new tool adding helpful damping to stop things from oscillating out of control? Or is it just adding friction that slows everyone down? Are we making our good architecture a deeper basin of attraction, making it easier to fall into? Or are we just adding noise that scatters everyone's effort? So I'll leave you with this one question to take back to your own work. Think about the project you're on right now. What's its energy state? How much chaotic motion is there? How strong are your constraints? Is your team stuck in cowboy chaos, or are you in resonant flow? What is the total stress, the Hamiltonian, of your project? And what's the one thing you could do tomorrow to start bringing that number down? Thanks for watching.